Hello, my name is Thomas West. My student number is 1904478 and today I will be presenting the wing I've designed for a small RPV drone, along with its design process and any improvements I've made along the way. So the aircraft we are designing the wing for is a small flying wing remotely piloted vehicle like the EBSQ agricultural drone, as you can see in the photo on this slide. The benefits of using a flying wing design is it reduces weight of the aircraft and drag, will make our plane more efficient, what is important as the aircraft is battery powered. And of course, as there is no empennage or fuselage, the stability of the aircraft is reduced, and that's why winglets are implemented to improve the aerodynamic stability of the aircraft. So the information I've calculated on this aircraft is that the all-up weight of the aircraft is equal to 22 kilograms. The cruising altitude of this aircraft is 290 meters, and the cruising velocity is 30 meters a second. So with this information, we are going to use a series of mathematical equations and information from different aircraft designs to design the best wing for our aeroplane. So the first step of the wing design process is to calculate the aircraft's lift coefficient. This is essential in the design of our wing. The graph on the right shows the wing loading plotted against the mass of existing aircrafts. Using our aircraft's mass of 22 kilograms, we can see that our wing loading is equal to 9 kilograms meter squared. And if we multiply this by gravity, we get a value of 88.29 newtons. Also at our cruising altitude, the pressure is equal to 0.96 atmospheres and the air density is equal to 1.19 kilograms meter cubed. So using these values with the equation below, we can calculate a design coefficient of lift equal to 0.164. So using this graph, we can calculate our aircraft stall speed, and then we can substitute our stall speeds into the equation for V, and then we can get our maximum lift coefficient, what is equal to 1.83. So using our designed coefficient value of 0.16, we can substitute this into the value in the equation for lift, and we can get a value of lift, what is equal to 214.46 newtons. When divided by the value for gravity, we get a mass value equal to our all-up weight. So this is the perfect designed coefficient of lift. Now the next step was to pick an appropriate aspect ratio. However, this is where I made my first mistake. Using the plane's cruising velocity, I selected a value of 28.3 from the graph for the aspect ratio, what was too high, what caused the wingspan to be very big and the chord length to be very small. The reason I chose this value was because similar aircrafts that had a cruising velocity of 30 meters per second had this aspect ratio. However, these aircrafts were aircraft such as gliders, what really needed long wingspans, whereas our remotely piloted vehicle needs a very small wingspan to be carried by a single person. Now it's time to calculate the dimensions of our aircraft. This step is where I identified a problem with the value of our aspect ratio due to the value of the wingspan being too big. To calculate the wingspan, we first need to divide our aircraft's mass by our wing loading to calculate a total wing area of 2.44 meters squared. Then, using the equation below, we calculated a wingspan of 8 meters, followed by a chord length of 0.293 meters. But not to worry, I improved our aspect ratio in a later stage of designing. Now it's time to select the best aerofoil for our aircraft. I selected a 5-digit series aerofoil due to them having a higher lift coefficient and a low pitching moment compared to other aerofoil series. I decided to go for the NACA 23012 because it had the highest maximum lift coefficient out of all the existing 5-digit aerofoils, even though it only had a maximum lift coefficient of 1.76, what is 0.07 away from our desired value. I was sure this aerofoil was going to meet our specific requirements compared to any other existing aerofoil out there. So to ensure that this is the best aerofoil for our aircraft, we tested its aerodynamic capabilities in a program called XFLR5. We first needed to set up some parameters like the wing's Mach number and its Reynolds number, at its cruising altitude. For this, we got a Reynolds number of 580,000 and a Mach number of 0.08. So once all the parameters were set up, we then tested how the aircraft's lift coefficient would change with a range of angles of attack. Below is a graph to show the aerofoil's aerodynamic capabilities. We can see that the aerofoil reaches a maximum lift coefficient of 1.76. We have an excellent stall angle of 18 degrees, and overall we can tell by this graph that this aerofoil is going to work great for our aircraft. Shown on this slide is a 3D printed model of our airfoil to show how the wing would look like. To make this, we used an Adventure 4 series 3D printer. It took 41 minutes to build, and it is created out of a material called PLA. The reason I have removed such a large section of material from the middle of the airfoil is to reduce the overall wing's weight as much as possible to make the aircraft more efficient, while still providing good structural strength to the entirety of the wing. This area is also a good space to store electronics of the aircraft. As there is no fuselage, the wing needs to hold all the electronics for the plane. So back to the aspect ratio. I reduced the aspect ratio down to a value of 3, what is a similar aspect ratio for general aviation aircrafts. So then this gave us a new wingspan of 2.7 meters and a core length of 0.9 meters, which is much more suitable. So the final thing to do is determine the final shape of the wing, like calculating its wing taper ratio, sweep, incidence, and dihedral angles. So with our wing, we have a taper ratio of 1. Having a taper ratio of 1 improves the overall aspect ratio of the wing as it has more wing area. Using data on the previous aircrafts, I have determined the best sweep angle for aircraft is 45 degrees. To calculate the wing incidence, I used a value of 1.64 degrees. This was calculated using the graphs back on slide 7 and calculating the ideal angle of attack using our ideal lift coefficient value of 0.3. And for the dihedral angle, I used a value of 8 degrees as this will improve our maximum lift coefficient. Now the shape of the wing has been formed, we can calculate the coordinates of where the aerodynamic center is located. I've calculated this location to be 0.675 meters along the wingspan and then 0.9 meters down from this location. So on this slide, I am showing a modelled version of our wing in XFLR5, with the winglets already set at a dihedral angle of 30 degrees. On the right is a representation of how the lift distributes over our wing at an angle of attack of 25 degrees. We can see that the lift distribution is almost elliptical throughout the whole wing and has an Oswald's factor of 0.976. To improve this factor, reducing the angle of the winglets will optimize the lift distribution over the wing, making it more elliptical. The final step is to test our wing's aerodynamic capabilities for a range of Reynolds numbers and angles of attack. We can see down below the sets of data our wing has produced. We can tell from this data that our maximum lift coefficient is 1.4, what is below our original aerofoil's maximum lift coefficient. However, we have a stall angle of 26.5 degrees, what is a major improvement from our airfoil stall angle. There is some other information listed on this slide down below. If you're interested in any further details of our wings capabilities, feel free to read it and pause the video now. Overall, I feel like I have made a great wing for this aircraft. It has a great maximum lift coefficient of 1.4 and great stall characteristics. It is lightweight and meets our original cruising conditions when travelling at a 0-degree angle of attack. However, it does not meet the theoretical maximum lift coefficient that was calculated at 1.8 back on slide 4. Some ways to improve the wing's maximum lift coefficient is using a different aerofoil with a thicker camber, increasing the dihedral angle, or even introducing flaps into the design. However, I feel like we have a good middle ground for all the properties of our wing. If we start raising the maximum lift coefficient, the stall characteristics of the wing may be compromised. So a maximum lift coefficient of 1.4, along with great stall characteristics, is definitely the best choice for our aircraft. Okay, so that concludes my wing design. Thank you so much for listening. I hope you can agree on my choices I have made, and I hope you enjoyed the presentation. Thank you very much for listening. Goodbye.